All right, so welcome to an introduction to probability. So you should be free to ask questions at any time you want. The goal is to just explain some of the key basic concepts that will be useful for mathematical modeling, useful for some basic stuff in finance. And so obviously we're not going to do an entire course in just 1 hour, but this is a chance to get some of the basics. I'm trying to just there you go, get rid of it. Okay, so intro to probability. So the first things you often see in probability is basic counting. So trying to figure out what is the probability of something happen, you often look at number of successes in the number of attempts. And that's a good way to try to estimate what is the likelihood of something. Now, obviously, the more observations you have, especially if they're independent, the better chance you have of truly seeing what's going on. If I flip a coin, what are your estimates for the probability of success after one flip? I'm sorry? What are your possible estimates for the probability of a success after flipping a coin once?
1 and 0.
1 and 0. Either it's always heads or it's always tails. That's all you're going to be able to see if you flip a coin once. So the question is, as we flip the coin more and more times, we start to have a better sense of what's going on. And you often have results called the central limit theorem. Is the phrasing at least familiar to people? Central limit theorem? So that if you have a lot of observations, let's say you have x1, x2, ... xn, these are IID. This stands for independent, identically distributed random variables. So they're all drawn from the same distribution. As mathematicians or as pure mathematicians, we often like to see what is the weakest set of conditions we can claim or assert for these random variables and still have the conclusion we want hold. In practice, however, it's frequently not necessary to really worry about too much about that. Let me take it out of battery mode so that it stops going into screensavers often. Okay, so you can of course come up with as weak conditions as you are able to, and then that means your result is more generally applicable, which is great. There's whole slews of generalizations where they don't have to be identically distributed. They don't have to necessarily be independent. There can be some small dependencies, but you've got to be careful. If x1 equals x2, then what do you know about x1 plus x2? That's the same as what? So if x1 is the same as x2, so imagine I have two die that are connected. And so they're aligned the same way. And so when I roll them, x1 and x2 are always going to have the same value. What do you know about x1 plus x2?
It's equal to x1 or x2.
Nope, 2x1. So it's just going to be 2x1. What if x1 equals negative x2? Then what's true about x1 plus x2? It's just always going to be 0. So when there's dependencies, you can have very strange things happen. If I consider a coin, we sometimes have a heads as a 1 and a tail as a -1. Sometimes we do a tail as a 0. The advantage is this way, the head and the tail are opposite. And you can do things like random walks and just see how far you are. You don't want to have things like heads and tails because then you can't add them together. You can't add 2 heads and a tail, but you can add 2 plus ones and a -1. So if you have a random variable that's heads half the time and tails half the time, if you denote it by 1 and -1, that has the same distribution as the negative of that random variable. Because if I only take on the values 1 and -1, each with probability 1/2, that's the same as taking on the values -1 and 1 with the probability 1/2. So I could have x1 and x2 having opposite distributions, but they could be independent. Can you give me an example of a +1, -1? Well, I'll just do it. Imagine I flip a coin. What's on top is my x1, and what's on bottom is x2. And that would be a great example of your completely dependent random variables. You know one, you know the other. The probability that the first one is a head or a tail is the same as the probability that the bottom is a head or a tail. It's just they have information together. So the more connections they have, the harder the analysis becomes. So what the central limit theorem says is one of the most important distributions is the normal, the Bell, the Gaussian. Whenever you have this many names, it's important. So we write it as mu sigma squared n for normal. Mu is the mean. Sigma is the standard deviation. And sigma squared is the variance. Has everyone at least seen these words? Standard deviation, variance. Everyone has seen them. Excellent. So it always becomes an interesting question, which quantity do you want to study? So if I ask you for how tall do you think the average Williams student is? Anybody want to give me an answer, roughly? 5'10".
Or both men, or, yeah, man, woman, both.
Whatever. I don't really care. I just want a number. So, man, okay. Average Williams male is 5'10". Okay. Do you believe it's exactly 5'10"? So what kind of units will you give me for the fluctuations about it? Inches, right? So we're probably measuring things in inches or feet. We would do something like that. Standard deviation and mean have the same units. The variance has the units of whatever it is squared. This is why the square root of the variance is the more natural quantity to study. It has the same scale as what you care about. In terms of looking at things mathematically, we often look at errors by looking at observed minus predicted, and then we square things. And the reason is we don't want positive and negative errors to be canceling with each other. And so it becomes more natural to just study the squares of things. But then when you're trying to combine at the end of the day and talk about some quantity that you care about, it's the wrong scale. So we take the square root. And so the central limit theorem says, let's let z be x1 plus x2 plus dot 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 plus xn minus n times the mean divided by sigma square root of n. And so we'll talk about exactly why we're doing this later. But it turns out the mean of z is 0. The standard deviation of z is 1. And z, well, we'll call it maybe zn. And zn converges to a normal 0, 1 as n goes to infinity. So this is called the standardization of a random variable. A lot of this is just so that we compare apples and apples. So if I have each value of x1, x2, x3, if they're all independent, if on average each one of them takes on the value mu, then I would expect after doing it n times, I would be at n times mu. If each one is on average 3 and I do it 10 times, I would expect to get a result of 30. The question then is, what is the scale of fluctuations? Well, it makes sense that the more you do, the larger the fluctuations will be. If I do things 1,000,000 times, let's say I have a fair coin. How many heads would you expect to have if you flip a fair coin 1,000,000 times? 500,000. How many heads would you expect to have if you had 10 billion coins? 5 billion. Do you expect the fluctuations around 10 billion flips will be tighter than about 1,000,000 flips or wider? Do you think the range of values that you'll be seeing? It makes sense that the more you're doing this, the more things are going to be spread out. So this is the first concept we want to understand is how do things spread out as we do things more and more? And so this leads to the concept of expectation. And so you could do things in either the continuous case or the discrete case. I'm going to mostly focus on the continuous case here. So let's say x is a random variable with density either f of x or p. When you have lots of random variables in play, it's often good to just put in subscripts. You can quickly look down and say, oh, this is the density that goes with this random variable. So I can quickly look. What does this mean? It means p of x is non-negative. The integral of p of x of, say, x dx from minus infinity to infinity equals 1. So something happens. And the probability that x takes on a value between a and b is just going to be the area under the curve from A to B. So if this is my probability distribution, and I give you here's A, here's B, the area under the curve from AB would be the probability I take on a value between A and B. This is one of the main reasons why you take 3 classes in integration. This is why you have Calc 1, Calc 2, Calc 3. Calculus allows us to calculate probabilities. Now, in general, when you're going into finance, you might have 360-dimensional integrals to do, which is going to be a tremendous challenge. We're not going to be able to get these integrals in closed form. The biggest lie, I think, in any math class you'll ever take is Calc 2, where you leave the class believing you can integrate. You can't. Don't worry, we can't either. We have to really work hard to come up with very nice functions that have antiderivatives, so you have these exact answers. In general, you can't write down an exact answer for something. So the next question is, once we have these probability distributions, what can we do associated to it? So you might remember Taylor series. If I give you a nice function f, then f of x is equal to the sum, n goes from 0 to infinity, of the nth derivative of f at 0 over n factorial times x to the n, or more generally, if you want to go around some other point, the nth derivative at a over n factorial x minus a to the n. And so the idea is if your function is nice, if you know the derivatives, then you know the function. Unfortunately, there are functions that are infinitely differentiable where all the derivatives exist and the function does not agree with its Taylor series expansion, except at 0, where it's forced to agree, because if you take x equals 0, the only term that survives is the constant term.
What's one example?
So this is either one of the best or worst functions in all of mathematics. So g of x is e to the negative 1 over x squared if x is not 0, 0 if x equals 0. If you try to plot this, it's going to be just incredibly dying at the origin. I mean, if you take x to be 1 over 1,000, this is going to give you e to the negative 1,000,000. So this function just crashes to the origin. If you use L'Hopital's rule, you have to go back to the definition of derivative in L'Hopital. You can show all the derivatives as 0. So what this means is at time 0, I'm at the origin, my speed is 0, my acceleration is 0. Does anybody know what the rate of change of acceleration is called? The jerk is 0. I think those are the next ones, yes? Yes. And so all of these are 0, but yet the function moves. And so things like this are absolutely horrible. So next year, I might be teaching complex analysis. And complex analysis does not allow functions like this to exist. So this, if you look at the generalization of this to complex analysis, where you replace x with z, the function isn't even continuous. In complex analysis, if a function is differentiable once, it's infinitely differentiable, it equals its Taylor series. None of this shit can happen. That's a technical term. Okay? Completely different. All the bad functions vanish. In probability, we have to worry a lot about issues like this, where do things converge? Does this result hold? And you have a lot of machinery that's needed to deal with stuff. So if I give you a nice function, however, you should hopefully have seen in calculus that it's given by its Taylor series. So does anybody know any famous Taylor series?
Oh, yeah. Physics.
Physics.
Oh, so e to the x.
E to the x.
Yeah.
So you have e to the x is the sum, n goes from 0 to infinity of x to the n over n factorial. And if you put in x equals I theta, you get e to the I theta is cosine theta plus I sine theta, and you get your series expansions for sine and cosine. There's a tremendous wealth. You can get every trig identity from this. E to the I theta, e to the I phi is e to the I theta plus phi is cosine theta plus I sine theta, cosine phi plus I sine phi. Expand everything out, now you have your double angle formulas. Incredibly powerful what you can do. What we want is we want an analog of this idea of Taylor series for probability distributions. So for Taylor series, we're associating a nice string of values. The value at 0, the first derivative, the second derivative, the third derivative. What are we doing in probability? We're looking at moments. So the expected value of x to the n is going to be the integral from minus infinity to infinity of x to the n times its probability density dx. Or more generally, the expected value of some function of x is going to just be the integral from minus infinity to infinity of that function times the density dx. Now, of course, these integrals will not always exist. But the hope is that you have a nice distribution where these exist and it can start giving you some useful information. So can anybody give me an easy choice of n? Easiest choice you can think of? Yes. So if we take n equals 0, we get the expected value of 1. What should the expected value of 1 be?
I assume the expected value of a constant is just the constant.
The expected value of a constant should just be the constant. If I give you a random variable that always returns 1, what should it return? 1. And if we look at the integral, we'll be integrating from minus infinity to infinity of the probability density. But we know every probability density equals to 1, integrates to 1, so we're done. Okay, building on this success, what's the next value we should look at? So we just did n equals 0, 1. So now we want the expected value of x. And that's going to be the integral from minus infinity to infinity of x times the density function dx. And that may not always exist. But if it does, we call this the mean. And we write mu or mu sub x. So, for example, if I give you the expected value of x, and let's say that's a normal with mean mu variance sigma squared, this would be integrating from minus infinity to infinity of x. The normal distribution has density 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx. What do you think? Has everybody seen this density for the normal? Okay, so this over here is the density for a normal distribution. Density for a normal distribution with parameters mu and sigma squared. So if you haven't seen this before, we're using mu and sigma squared as the parameters. What does mu represent for us? The mean. And what does sigma squared represent? The variance. What do you think the mean of a normal distribution with parameters mu sigma squared should be? So what should the mean be? Not 0. Nope. I'm giving you a normal distribution with parameters mu sigma squared. What should the mean be? Nope. It's just mu, right? Right? I'm giving you, I'm trying very hard not to say, I'm giving you a normal distribution with mean mu and variance sigma squared. I'm giving you a normal distribution with parameters mu and sigma squared. What should the mean be? It should be mu. If it's not mu, our notation sucks. Who knows what 1 over cosine is called? And what's 1 over sine called? Wouldn't you rather associate sine with? There's a reason why they don't do this. There is a reason why, but notation could be bad. This would be horrible notation if the mean is not 0. So let's prove that the mean is 0. So what we're going to do is we're going to do some change of variables. So proof. So change variables. Let's write. We're going to write x as x minus mu plus mu. Okay. So we get the expected value of x is the integral from minus infinity to infinity of x minus mu plus mu times 1 over 2 pi sigma squared square root e to the negative x minus mu squared over 2 sigma squared dx. So I can break this into 2 integrals, the x minus mu times this and the mu times this, right? And again, I'm writing it like this because this is a great way to work with things. I see I have an x minus mu, I had an x, let's write it as x minus mu plus mu. Now I've got the x minus mu like I had before. So continuing, I would get the integral from minus infinity to infinity of x minus mu times 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx plus mu, because I can just pull the mu because it's a constant outside minus infinity to infinity x minus mu, oh, sorry, no x minus mu, sorry, just 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx. Well, this is a probability distribution. This is a density. What do you get when you integrate a density? It's just 1. So we know this part over here is 1. And now for the other one, let's change variables. Let's let x minus mu equal t. So we now get the integral when x is minus infinity, t is minus infinity. When x is infinity, t is infinity. Dx just becomes dt because it's just a simple translation. So I get the integral from minus infinity to infinity of t, 1 over the square root of 2 pi sigma squared e to the negative t squared over 2 sigma squared dt plus mu. Can anybody tell me what this integral is?
Well, it's basically t times e to the minus t squared. So, oh, I can tell you t times e to the minus t, and then we can do the rest from there. But
Well, t times e to the minus t doesn't help us because we have e to the minus t squared. There's 2 ways to do this integral. One is I would do by a u substitution. If I give you e to the minus t squared, let's forget about the 2 sigma squared for now. The derivative of that would be e to the minus t squared, and the derivative of negative t squared would be minus 2t. Oh, good, that's basically what I have here. So I should be able to do a u substitution, and I should be able to evaluate it like that. You don't want to do a u substitution. I don't want to do a u substitution. There's a better way. What kind of function is this? This is an even function. If I replace t with negative t, the probability density doesn't change. It's symmetric about the origin. But t is odd. So when you look at the plot of this, the positive probability is canceled with the negative probability. So, again, if I plot things, here is a plot of the Gaussian. But now if I multiply it by t, maybe it's going to look, I don't know, something like this going, up and then down. It's odd. So the stuff from 0 to infinity cancels with the stuff from 0 to negative infinity. So integrand is odd, so the value is 0. And so we get that this is just equal to mu. So we showed that the mean of the random variable is just mu. We have to be a little bit careful. It's worth seeing the Cauchy distribution. This is one of my favorites. So let's let the probability density be 1 over pi, 1 over 1 plus x squared. So you have to remember that the derivative of arctangent of x is 1 over 1 plus x squared. And there's fun ways to prove that. This is how I get the normalization constant. This is clearly a non-negative function. It turns out the integral from minus infinity to infinity of p of x dx is equal to 1. And the simplest way to see this is to note that it's the arctangent. Why am I caring about this? Well, if I try to calculate the expected value, that'd be the integral from minus infinity to infinity of x 1 over 1 plus x squared dx. You want to say it's 0 because this is odd. Right? The positive integration cancels with the negative integration. The problem is this goes back to Calc 2 and how do you deal with improper integrals. So just because I write this down, I've got to be careful. What does it mean to be integrating to going to infinity? What it really means is I've got to consider the limit as a and b go to infinity of the integral from, say, minus a to b of x times 1 over pi 1 plus x squared dx. I have to look at all the ways I can go to infinity. And so if I take the special case b equals a, what do we get? So if b equals a, what's the integral from, say, minus a to a of an odd function? What would that be? That'd be 0. So we get 0 because it's finite. But if I take b equals 2a, I get the limit as a goes to infinity, the integral from a to 2a of 1 over x, of x times 1 over pi 1 over 1 plus x squared dx, because the integral from minus a to a canceled. So everyone see that the integral from minus a to a cancels, and I'm left with just the integral from a to 2a. This is approximately the limit as a goes to infinity, integral from a to 2a of 1 over pi x over 1 plus x squared. What is x over x? What's x over 1 plus x squared if x is tremendously large? But approximately what? How would you approximate x over 1 plus x squared? Yeah. Nope, that's too much of an approximation. When x is really big, how could you simplify the denominator 1 plus x squared?
Or make it x squared.
You could just make it x squared. When x is really large, x is a quadrillion. How many have been following the Elon Musk stuff? It turns out they just uncovered some emails where he said he would actually pay $44 billion and $1. Now, doesn't matter, right? The $1 is not going to make any noticeable difference, right? When you're looking at this, x is huge, the +1 doesn't really matter. So it's approximately x over x squared. What's x over x squared? 1 over x. All right, who remembers what the antiderivative of 1 over x is? Natural log. So this would just be equal to the limit as a goes to infinity, 1 over pi, the natural log of 2a minus the natural log of a. Well, now the log of the difference is the log of the quotient, so you just get the natural log of 2. So you get the natural log of 2 over pi. So depending on how I go to infinity, I can actually make this equal whatever I want. And this is telling you that you have to be very careful when you're doing a lot of these calculations. The mean does not always exist for random variables. For the Gaussian, it exists. It's exactly what you would expect. For a distribution like the Cauchy, which arises in finance. So it's not a coincidence that I'm saying this. It's not just pure mathematician love talking about it. If you look at Benoit Mandelbrot, a lot of his work in fractal geometry has been applied. With this wonderful book, The Fractal Misbehavior of Markets. If one of you emails me, I'll give you the link that you can then share with everyone. Some great papers that some of his colleagues have written about if you try to model Wall Street by a random walk of just basically tossing maybe a biased coin. Hopefully we're in a time where stocks move up with a higher probability than they move down. This does not do a good job. It doesn't talk about probability of unlikely events occurring frequently enough. So, most of the time things are fine, but every now and then you get these really big trade days where stuff happens far beyond what you would expect. And the question is, how often do these big days occur? And with the random walk of tossing a coin, it doesn't seem to give you the right probability as to what you would expect for what's happening in the real world. And so if you're interested in stuff like this, this is really great stuff to see, highlights some of the great difficulties. So we talked about the mean. The next thing we can look at is the variance. And so the variance is defined as the expected value of x minus mu squared, or the expected value of x minus the expected value of x squared. And we write this as sigma squared. So this is not the same as the second moment. The second moment is just the expected value of x squared. It's the same if mu is 0. So everybody has seen the concept of variance and standard deviation. So this is talking about fluctuations about the mean. If I add $1,000 to everyone's bank account, the fluctuations about the mean don't change. The mean changes, the location from where the action is happening changes, but the fluctuations about the mean don't change. And so when we're trying to get a sense of how are things distributed about the mean, it's not a bad idea to just subtract the mean. This is the idea behind standardization. I want to be able to compare apples and apples. So whatever you give me, let me just adjust things and make the mean be 0. And now I'm talking about fluctuations about that. The next thing is then you change your scale, if possible, to make the standard deviation equal to 1. And so we would now calculate something like this. So if I gave you the Gaussian, what do you think you would get if I integrated x minus mu squared times 1 over 2 pi sigma squared square root e to the negative x minus mu squared over 2 sigma squared dx? What do you think I would get for the variance of a Gaussian with parameters mu and sigma squared? So what should I get? I should get sigma squared. And if I don't get sigma squared, I've made a horrible, horrible mistake. So here, you're going to have to integrate by parts. And so let me just. So integrate by parts. First, of course, you could let t be x minus mu to simplify things a little bit. And so now we have the integral from minus infinity to infinity of t squared. I'll put out the square root of 2 pi sigma squared over here, e to the negative t squared over 2 sigma squared dt. I could get rid of the sigma squared. I could let u equal t over sigma. So du would be dt over sigma. So dt would be sigma du. And again, I just want to do some of these calculations just so you get a sense of, if you have to do these integrals, how do you handle them? I might as well just change variables to make my life a little bit easier. Okay, so I replace dt with sigma du. Oh, that sigma is going to cancel the sigma outside over there because that sigma squared square root is just a sigma. So when I replace dt with sigma du, the sigmas cancel, and I will get 1 over the square root of 2 pi integral minus infinity to infinity of t squared. Okay, well, what's t squared going to be? That's going to be sigma squared u squared. Sigma squared u squared e to the minus u squared over 2 du. Okay, and now we want to integrate this. The trick is to write it as u times e to the minus u squared over 2 u du. And if I do it like this, this is set up very nicely now for integrating by parts. What's the derivative of e to the negative u squared over 2? It's e to the negative u squared over 2 times negative u du, or just times negative u. And so the trick is to actually replace the u squared like this and reduce it to things you already know. So it's a nice exercise. Try to see if you can figure this out. Okay, the higher moments start talking about more shapes of the distribution. And so the big thing in the central limit theorem is that if x1 dot 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 xn are nice, then we said zn, which is the sum of the x's minus n times the mean divided by sigma squared of n converges to a normal with mean 0 and variance 1. So this tells us there's a little bit more we need to learn about expectation. if I give you a combined random variable, I should be able to calculate maybe its moments, its expected value, its variance in terms of its constituents. So we need some lemmas. So the first lemma is the expected value of x plus y is the expected value of x plus the expected value of y. This makes sense. If on average x is 5 and on average y is 8, then on average x plus y is 13. This is the 1 hour class. We're not going to do a proof, but this is very reasonable. This does not need independence. So we're not assuming independence. Okay. The next lemma is the more interesting one. The expected value, the variance of x plus y is the variance of x plus the variance of y if independent. And what do you think the variance of ax should be in terms of the variance of x? No, a squared. So think about units. So one thing is also, if a is negative, you can't have a negative variance. So what we're going through is, when you look at the definition of the variance, we're looking at a quantity squared. So if I multiply x by a, I'm going to get an a squared that I pull out. So the hope is that if I have some independent random variables, the variance of a sum is the sum of the variances. And so if I keep doing a bunch of independent trials of the same thing, the more I do, the more spread out I expect it to get. If the random variables are not independent, all bets are off. If you've seen covariance, this is where the covariance terms start to come in. Life becomes much harder. When I look at this quantity Zn, what do you think the expected value of Zn should be? 0. And what do you think the variance of Zn should be? 1. If that's not the case, boy, are we in trouble. And so let's look at this calculation. So the expected value of Zn is the expected value of x1 plus xn minus mu over sigma squared of n. I may not have isolated all this before. If I multiply a random variable by 3, what happens to the mean? What's that? Right. So instead of measuring things in yards, if I measure things in feet, then my value will be 3 times. If I subtract a constant from you, what should happen to the mean? So if I subtract 5, what should your new mean be? 5 less. So we immediately get that this should be 1 over sigma square root of n, expected value of x1 plus xn minus n times mu. Right? I can pull out the factor, and because n mu is a constant, I can just subtract that. Now we use the expected value of a sum as the sum of the expected values, and we'll get the expected value of x1 plus the expected value of xn minus n mu. But each of these is just equal to mu. So we just get 1 over sigma square root of n mu minus n mu equals 0. The variance calculation is a little bit more involved, but you can similarly show that the variance of this is 1. So what we've done is we've adjusted our sum x1 through xn so that it now has mean 0, variance 1. I am significantly older than all of you, so some of these you should know. What's the log of x times y? Does anybody remember the nice formula for that? Log x plus log y. So there's a bunch of log rules, but the last one is the one that most people forget. The change of base formula. So the log of x base b is the log of x base c divided by the log of b base c. The reason this is so valuable is people's jobs used to be calculating log tables or calculating values of areas under the normal distribution or this or that. This tells you if I know the logarithms in one base, I know them in another. So if I know the logarithms base c, I can now get them in base b. I only need to figure out logarithms in one base. This is extremely valuable. It allows you to convert from one to another. Think of that as what we're doing with the standardization. I want to be able to compare things. I'm going to always adjust things so that my mean is 0, my variance is 1. This is where the universality in the central limit theorem is coming from. Why, no matter what random variables you take, when you add them, do you get this normal distribution for the sum? Why are the sums normally distributed? It turns out when you go through the proof, because I can always adjust nice probability distributions to have mean 0 and variance 1, I don't see the shape of the distribution until I get to the third moment. And those come in as lower order correction terms. Right. So let's do an application of all of this. How many of you have ever seen weighted portfolio management theory? Okay, great. So let's do a weighted portfolio. Let's say we have two independent stocks. And they both have mean return of mu, and they have variances sigma 1 squared and sigma 2 squared. What is your goal when you're investing? To maximize returns. So I wish I could actually do this as a non-theoretical exercise. I apologize, it's going to have to be a theoretical exercise. I will give you a 49% chance of getting $1 million by flipping a coin. So 49% of the time, you get $1 million. 51% of the time, you get nothing. Okay? Or I will give you 100% of the time, $499,000. Which has a better expected value? I'm sorry? Well, the first one is 49% of the time, you get $500,000.
490.
So I think the 499 would be a little bit better. Now let's make it a little bit harder. Let's say 50% of the time, I'll give you $1 million, and 50% of the time you get nothing. Or 100% of the time, you get $450,000. So the expected value now is quite clear that it's $50,000 less. Which would you rather do? One toss for $1 million, but if it comes out bad, you get nothing. We are risk averse. Well, most of us are. Let's say it's Elon Musk. Well, what might he choose? He might do the coin toss, because for him the $1 million is noise, and so it's really not there for us. And if it's not the case for you, we need to talk afterwards. The $1 million, 50% of the time, how much additional benefit does that second $500,000 give you over the risk of getting 0? So how many people would choose the 450 guaranteed? Right? I'm sorry? Tossing is fun, but and then again, it's just how much will your life change, especially when you factor this thing called taxes. So for the additional 500,000 you get, how much of that are you going to lose? What is your net gain? How much change does that first $500,000 give you versus the second? The marginal utility of the first $500,000 is different than the marginal utility of the second. This was supposed to be for a quant club, so I wanted to end with a real example of things you should be thinking about. It's not just pure math. You have to take into account what are you going to do with it. So when you say your goal is to maximize revenue or profit or returns, that's not a bad start. But let's think about that more. How much are you willing to do? Now, again, what if I told you we're going to do this 1,000 times? And for 1,000 times, we'll flip a coin. And if it's heads, you get $1 million, tails, you get nothing. We'll do this 1,000 times. Or I'll just give you 450,000 times 1,000. Which would you rather do? Yeah, at this point, I'd flip the coin. Yeah, I'm going to occasionally get some tails, but I would expect to get more money by doing that. And I'll get at least so much money with incredibly high probability, I'm not worried. So another thing we are often concerned with in finance is not just maximizing revenue, but as you said, is risk aversion, is we want to minimize risk. So if you have two strategies and they have the same expected return, and one of them has significantly less risk than the other, which one should you choose? The less risky one. So now when things are being priced, the more risky alternative could give you more money, but at the cost of you might get nothing. And so when they're trying to figure out how much should you give someone to invest in various things, this company could go belly up, but if it becomes the next Facebook or Amazon, I'm going to become richer than all of my dreams. How much is it worth? When you're trying to decide, is it worth going to a startup and not going to an established company? Well, if the startup really clicks, and I might want to say, well, even if it doesn't, I'm going to get some good experience. So these are calculations you need to do. All things equal, if there are two portfolios and one has less risk than the other and it has the same return, we would rather take the one that has less risk. Now, sometimes one will outperform the other just through random fluctuations. So I'm going to do the more general case as long as possible where sigma 1 and sigma 2 are different. And then to simplify some of the calculation later, we might assume that they're equal. But I have two stocks. They have the same expected return, and they have two different variances, sigma 1 squared and sigma 2 squared. If you were going to invest, which one would you choose and why? Okay, so if one stock choose x1 as sigma 1 is less than or equal to sigma 2. If two stocks, maybe you do some kind of weighted portfolio. Maybe you do lambda x1 plus 1 minus lambda, lambda, 1 minus lambda x2. So what can you tell me about where does lambda live? What are the possible values for lambda? Yeah, I'm trying to allocate what percent of my investment is x1, what percent is x2. So 0 less than equal to lambda less than equal to 1. And so the question is, if I have two independent options, is it possible that by doing some kind of weighted investment, I could actually lower my risk without decreasing my expected return? What am I assuming about these two stocks? Independent. So if you remember the financial crash in 08-09, a lot of the issue was the fact that certain things were assumed to be independent that were not. And so when this sector went down, it dragged other sectors down with it. When these housing prices fell, they dropped other ones with them. So the independence is a huge assumption here. So let's apply what we've done today. So let's calculate the expected value of lambda x1 plus 1 minus lambda x2. So what's the expected value of a sum? Sum of the expected values. And the expected value of a constant times the random variable is the constant. So this is just going to be lambda expected value of x1 plus 1 minus lambda expected value of x2. So this is going to be lambda mu1 plus 1 minus lambda mu1. I'm sorry, I guess I'm just calling it mu. Okay, this is a pretty easy calculation to do. The lambda mu's cancel, and you just get mu. So not surprisingly, there is no change in your expected value of your portfolio. Let's now do the variance calculation. So the variance of lambda x1 plus 1 minus lambda x2. What's the variance of a sum of independent and random variables? The sum of the variances. And then constant times the random variable, you pull out the constant squared. So you get lambda squared variance of x1 plus 1 minus lambda squared variance of x2. So this is lambda squared sigma 1 squared plus 1 minus lambda squared sigma 2 squared. And now what do we do? We could, but what's our goal now? Goal is to minimize. Is minimize. Subject to 0 less than equal to lambda less than equal to 1. Anybody have any idea how we might minimize this? I'm sorry? Lagrange multipliers is when you have a constraint, not second derivative, first derivative, right? So check endpoints. Find critical points. So let's call this g of lambda. So just find places where g prime of lambda equals 0. So just in the interest of time, I'm going to just do the special case. Let's assume sigma 1 squared equals sigma 2 squared equals sigma squared. So the two stalks are equal. You should be able to tell me what the answer is without even doing the calculation. What value of lambda? There's only a couple things that could work. So one possibility is it doesn't matter. Any value of lambda would be the same. Or what's the only value of lambda that might make sense? .5, because if the two things are the same, we're biasing it in favor of 1 over 2. That should be the same as then biasing 2 in favor of 1. So it's either every value of lambda gives you the same, or lambda equals 1/2. So we have g of lambda is going to be lambda squared sigma squared plus 1 minus lambda squared sigma squared. G prime of lambda is going to be 2 lambda sigma squared plus 2 1 minus lambda negative 1 sigma squared, right? So we get, I can pull out the sigma squared, I get 2 lambda minus 2 times 1 minus lambda. Yes? So we get sigma squared, I can pull out a 2, and I'll get lambda minus 1, 2 lambda minus 1. Yes. So g prime of lambda equals 0 implies 2 lambda minus 1 equals 0, implies lambda equals 1/2. And you check the endpoints as well. If I take lambda equals 0 or lambda equals 1, the variance is just going to be sigma squared. Right? So this is now actually blocking. Okay. So we agree that if I just take lambda equals 0, I get sigma squared. If I take lambda equals 1, I get sigma squared. If I take 1/2, however, I would get 1/4 sigma squared plus 1/4 sigma squared is sigma squared over 2, which is less. So this is amazing. If you have two portfolios, it makes sense. Your risk should be decreased. One of them might go up, one of them might go down. The more of these that you have, the more likely it is that you're going to be coming in around the mean. The less likely it is that you're going to have a really great performance or a really disastrous performance. So this is one of the simplest applications of basic probability moments and whatnot to portfolio theory to trying to find investments. The biggest assumption here is that everything has to be independent. As soon as you lose the independence, this argument is completely gone. Okay, so the goal was for 1 hour lecture. It is 10:59 right now. Is there any other topic you really wanted to see today?
No, I think that's. Can I ask
Yes.
you, in what cases might be better to model stock growth or like asset growth in discrete time as opposed to continuous time?
Well, here right now, we're really not talking about discrete versus continuous here.
Right.
So here we're basically looking at, this could be what happens after one period.
Yeah.
We're talking more about the returns being modeled continuously. So is your question as to when is it better to model?
So like say you have like but you model it like binomial, like a binomial model.
Well, right. So that's more the outcomes.
Right.
Right. So for a lot of things, it is better to do a discrete model when you only have a discrete set of options that can arise.
Is there a real case? Like,
Well, here's the thing. I mean, if you look at a lot of your big businesses, it's so big, the numbers span so many orders of magnitude, it's not bad to just approximate things with a continuum. If you have a smaller number of things, if you're trying to model maybe how many hurricanes do we have, you would probably want to do that with a discrete random variable. And maybe you're in a financial insurance industry, and the number of hurricanes that hit is going to greatly impact your profits, and you're trying to figure out how much should you charge for insurance. Well, you need to be able to estimate how many hurricanes are going to hit, but it's not just the number of hurricanes. What else would you need to know?
How they like hit one spot a lot of times.
Are they hitting one spot? What else?
How powerful.
How powerful? And so maybe some small hurricanes, they say, oh, California, there was an earthquake, what was it, 3.2? Oh, 3.2 doesn't count. It's until it's at a certain level, the event doesn't really matter. And so when you're doing something like that, that would clearly be a discrete. One of the more difficult things is if you break things up into categories, anybody know how many categories we have for storms and hurricanes? I think it's 5. I think it's, you go category 1 to category 5. So with that classification, if you're right on the boundary, that's going to be a huge difference. There are a lot of things in life which are right on the boundary. If you're going up for tenure, it's 0 or 1, you get it or you don't. How many of you have taken an AP exam? Yes, 5, 4, 3, 2, 1. If you don't get the 3 or the 4, depending on where you're going, it's basically worth nothing. And there's really not much demarcation at times between somebody who just got a 4 or just got the 5. I'm sorry, just got the 4 or got a very high 3. Just got the 5 or just missed and got the 4. So when you have discrete breaks like this, it's often very bad in terms of trying to understand and model what's going on because you have these sharp cutoffs. It's oftentimes a lot better to have some kind of slow, variation and say, I'm not going to have this hard classification. I'm going to have this kind of continuous spread. It does make things easier for some things, but of course it's not natural for others. I know we have some baseball players. Yep. You're not going to really say, hey, it was a 90% strike, 10% ball. So the count is, 0.1 and it's got to be called ball or strike. So there are a lot of things where you have to use discrete modeling. But mathematically, we have 3 classes in integration. We've developed a lot of techniques to handle how to calculate integrals. And so whenever possible, we like to try to convert things to the continuous case because it's just a little bit easier to analyze. All right, so let me stop the recording.